To keep a building standing during an earthquake, engineers need to know exactly how the ground beneath it is going to move. They have to map out the intense stress and displacement of the soil while the earth is actively tearing itself apart. This glowing 8-bit equation is the wave equation. It is the mathematical rulebook for how seismic energy travels, and it is what we call a partial differential equation, or PDE. A PDE is simply an equation that describes how something changes across multiple different dimensions at once. In this case, those dimensions are time and depth. To solve this PDE, you have to calculate how the shaking changes as the seconds tick by, while simultaneously calculating how it changes at every single layer of dirt and rock deep underground. You are forced to track both variables simultaneously. If the soil at 50 feet down shifts, it alters the shaking at 40 feet down a millisecond later. It is like trying to dodge two completely unsynchronized, highly chaotic attack patterns at the exact same moment. If you try to brute force the entire equation directly, calculating every depth and every fraction of a second, the sheer volume of connecting variables overwhelms standard analytical methods. To actually figure out if a structure will survive, engineers cannot fight both variables at once. They need a mathematical exploit to break the equation apart and isolate time from depth. The tool engineers use to bypass this complexity is the Fourier transform. It is a mathematical operation that takes a messy, complicated signal and breaks it down into its basic underlying rhythms. Look at this chaotic pixel art waveform. The Fourier transform shows us that this random, jagged earthquake isn't actually random. It is simply a stack of perfectly smooth, simple sine waves vibrating at different speeds, or frequencies, like 1 Hz, 2 Hz, and 5 Hz, all playing at the same time. When you isolate just one of those smooth waves, its behavior over time stops being chaotic. It becomes a perfect, infinite loop. You know exactly where the wave will be at any given second. In math terms, this repeating time loop for a specific frequency is written as e to the I omega t. The simple omega, represents the specific frequency, and the t is time. Because this isolated wave's movement is locked into that predictable loop, time is no longer a mystery. We know exactly what time will do. By pulling the earthquake apart into these individual frequencies, we strip away the unpredictability of the timeline. The dynamic, shifting threat becomes a static, pre-programmed condition. Now, we take that predictable frequency loop and inject it directly back into our original complex wave equation. We replace the messy, intertwined ground movement with our clean e to the I omega t cycle. Here's what happens in the equation. When you take the derivative, which just measures the rate of change, of that time loop, the messy calculus simplifies. The time derivative term, UTT, physically transforms into a simple multiplier, negative omega squared. We are left with an updated equation that has perfect symmetry. The exact same predictable time loop, e to the I omega t, now sits identically on both sides of the equal sign. Because those identical time loops appear on opposing sides, they completely cancel each other out. The entire dimension of time drops out of the problem. The surviving variables collapse together, leaving us with a much shorter, much cleaner piece of math. G u z z plus rho omega squared u equals 0. With the time variable permanently deleted, this is no longer a partial differential equation. It is now an ordinary differential equation, or ODE, an equation that only tracks a single dimension. That specific mathematical substitution wiped an entire dimension of physics off the board. We don't have to worry about the ticking clock anymore. We only have to analyze the depth of the soil. This mathematical exploit is the exact foundation of Shake, the industry-standard software that structural engineers use to model earthquake responses. Instead of fighting time and space simultaneously, Shake takes that simplified ordinary differential equation and solves it by moving straight up through the ground, calculating the physical physics layer by layer, from the bedrock to the surface. The software tracks the 1 Hz wave's journey upward through the dirt. Then it runs a completely independent calculation for the 2 Hz wave. Then it does it again for the 5 Hz wave. Once it maps how the soil amplifies or absorbs each individual frequency, Shake recombines all those separate layers of data. This builds a highly precise prediction of the total cumulative ground shaking that will hit the surface. Looking at this cross-section blueprint, you can see the final output. Engineers hand this precise surface movement data to architects, giving them the exact structural tolerances required to design a skyscraper capable of safely riding out the quake. Complex physical events easily overwhelm brute force calculation. Engineers solve the world's most daunting structural problems not by trying to calculate everything at once, but by systematically rewriting the mathematical rules to eliminate the variables entirely.